lateral faults on the planet. So we think that maybe tectonics is a more important factor than just chain. But this again needs to be investigated more fully. We're at the beginning of an adventure here, but we can't see the end yet. So thank you. I think Marcus has dropped off, but he did have a question, I believe, Wati, if we can reconnect with him.
Thank you, Tim. First of all, it's very interesting presentation from you. I also really appreciate that in the beginning you said that you consider yourself as a part of UNIPA family. So welcome.
Thank you.
So this question is coming from not from the biology side because I'm not biologist. But I was just wondering that you mentioned about how important the discovery of the fossil, especially the mammal fossil in the Hogerkop area. So how the discovery of this mammal, the fossil mammals, contributed to your, or let's say the claim that in the past we have like a connection between Hogerkop and also with the Australian continent.
Yes. Look, I started my career as a paleontologist, Marcus, so I started with the study of fossils, and I realised I was very fortunate in doing that because they are exceptionally important in understanding zoogeographic relationships and evolution. You're very fortunate as well at this conference, Marcus, in that Scott Hucknall and I believe some people from Flinders University will be contributing, and they are really the experts on this area in Australia today. You've got some of the really great people in that field contributing to this conference, so I'm very pleased to acknowledge them and to hear what they have to say. But it is important, and we can pioneer this field in the Vogelkop. I know you have a great geology department at UNIPA as well. Perhaps we need to have some combined field work with geologists and zoologists, looking in some of the most interesting rocks in the region, rocks of the right age, and we will find something. The stuff is out there, the fossils are there, they just need eyes on the ground to detect them.
Thank you, Prof. Tim and Pak Marcus. So, but maybe in the room, any question? No, yeah. But before we closing with that, I'm interested with the species Dactylonax camboyai, Professor Tim.
Yes.
So maybe please you explain the name is camboyai. It's I think family name from Mebrat. So there is the base of the name or maybe something else.
No, it is named for Mr. Camboy, who is he was a teacher, a school teacher, I believe, in the area in the Maybrat area in the 1990s when Dr. Ken Aplin was working on those archaeological finds, and he was so impressed with Mr. Camboy and his assistance to the project that he named this animal in his honour. So I know it's a very prestigious family, the Camboy family. I've met some members of the family on my last visit, and it's a very, very appropriate acknowledgement of the tremendous contribution of that family and the people of the Vogelkop in general to our understanding of biodiversity.
Yeah, thank you. Perfect, Professor Tim. Nice to hear that. Yeah, yeah. Ladies and gentlemen, I'm just want to say if the Professor Tim is he is author of a book on the New Guinea mammals. It must read for our student and then researchers from Papua. We will using that book. Yeah, that book is very interesting. And Professor Tim, yeah, do the time constraint, and then we will conclude the presentation and then discussion session at this point. But before it, we have a slogan in here, Pak Professor Tim and ladies and gentlemen, in in Indonesia say kita jaga alam maka alam jaga kita. Yeah, we protect nature and then nature will be protecting us. And then Papua Barat as the conservation province, yeah, we have a slogan too. Kalau bukan kita siapa lagi? Kalau bukan sekarang kapan lagi? If not us, who? And then if not now, so when? Let's to protect the mammals of the fossil crop. Yeah, there's the closing statement from me, and then we thank you, Professor Tim, and then let's give applause to Professor Tim for the presentation and this discussion for this session. So as a form of our appreciation and then gratitude to Professor Tim, the rector and then committee will they award a certificate to Professor Tim Flannery. We can give applause to Professor Tim. Thank you, Professor Tim. See you in the next time. Yeah.
Yes.
Yeah.
Next tahun depan.
Okay.
Sorry, maybe we can take a picture first.
Yeah, Professor Tim will take a picture all of before we take it up. Ready? Okay, 1, 2, 3. Yeah, one more. Sudah? Okay, thank you, ladies and gentlemen, and then Professor Tim. See you the next session.
Thank you.
Thank you so much, Professor Tim and Dr. Rawati Panjaitan. Now we move to another agenda. Let us continue with second keynote presentation session, moderated by Mr. Markus Haryanto Langsang, PhD. Please welcome Mr. Markus Haryanto Langsa, PhD.
Okay, thank you. For the second session, I will be the moderating. I will be hosting the second keynote speaker. I'll just check if the Dr. Neo already, oh yeah, he's already joined the room. Hello, Dr. Neo, can you hear me? Yeah, Dr. Neo. Yeah, he's in the room, but maybe I'll try to reach him by WhatsApp. Just give me a second. Oh, okay. All right.
Can you hear me now?
Yeah, it's good.
Okay, thank you, Marcus. I think the first thing I need to make sure is let me share my screen first.
For the
You know, in this Zoom session, I can I found it now.
Oh, okay. You just change your status.
Okay, yeah, I can share now. So let me share this one. Which screen are you seeing now? The one with
the left side is red, but the majority of the slide is in white.
Yes, but do you see my slide, or do you see this is in the display mode?
Yeah, that's
everything is okay.
Yeah, that's fine. We can see it.
Okay, so I think I can start
Yeah,
when
yeah. Okay, I'll just give a short introduction to audience about you.
sure.
Uh, so we are very pleased to and also honored to have Dr. C.G. Neil as keynote speaker. He's associate professor working at the Department of Environmental Engineering at University of Cincinnati, Ohio, USA, and he's uh, he's starting his position as an assistant professor at the university in 2023 until now, and then he's finished or achieved his PhD from Curtin University in Perth, Australia, the same university as I also graduated from this university in 2018. In terms of the publication, um, it's very productive. There are at least 40 publications in his resume, and I can assure you that all these publication, all these papers published in very high reputable journals. Currently, he has a project funding roughly around $1 million US dollar. So you can imagine how much is this in the rupees. He has many also academic position, especially become the board directors and also the editorial board, some of the journals, and also the faculty members in his college. So that's a quickly introduction about the speaker, our second keynote speaker. And I don't want to spend much time on this, so I will let you start giving your presentation. This time is yours, CG.
Thank you, Marcus. Thank you very much for the invitation to participate to this conference. So I understand that the conference is more related to biodiversity, but today I'm going to talk a little more about chemistry, because we know the interactions between human activities and also the environment. Those are the case in a lot of the domains in human development. I was talking with Marcus, and he introduced to me some of those activities going on, some anthropogenic activities going on, like construction, like tourism in your area in Papua. And because of that, we are impacting our environment for sure. So the topic I'm going to talk about today is some chemical called per and polyfluoroalkyl substances, which is called PFAS. I'm going to talk about the current status of the research and how dangerous they are to us right now, and how this could impact human health and also ecosystem. So, sorry, my name is, I forgot to introduce quickly. My name is Xi Jinliu. I'm assistant professor in the University of Cincinnati, and I work with emerging contaminants here. And we're very glad to participate to this conference. So Marcus already introduced a little bit of myself. I do have a slide, but I'm going to go very quickly over this one. So we are in the University of Cincinnati. I have a slide later on talking about a quick introduction of our program. I was previously in the University of Arizona, and then before that I was in Australia. So that's where I met with Marcus. So my background is in chemistry, and eventually looking at how contaminants and chemistry impact environment, how we can manage them. So the chemicals I'm going to talk about today, many of you might have heard of it, is the so-called forever chemicals. When we call them forever chemicals, most likely because we really have those chemicals in the environment, in our drinking water, any drinking water, in the rivers, in our swimming pools, in our soil. And it is forever also because they are very difficult to manage. You cannot destroy them because they are very stable. So these chemicals has been generated in the 1940s. by some chemical companies. At that time when these chemicals were created, they were great inventions of that time, even nowadays, because we use that a lot. So these chemicals are interesting because they have the carbon fluorine bond, which makes them extremely stable. Because they are stable, so we use them for a lot of purposes. They are so good. I mean, they are a great invention, of course, commercially. Also, because they are stable, when we discharge these chemicals to the environment, this cause issues. If they are so stable, they can be there forever because you cannot destroy them. So we have a lot of those chemicals detected in the US, in Australia, Europe, in China, in Japan, in many other countries. But I'm sure, because these chemicals are pretty much everywhere, but I'm sure you can, if you do the analysis, you have those chemicals in Indonesia, in Jakarta, or in Papua, all the places, they're all around. Because they have been used in so many different industries.
Recording in progress.
Maybe you don't have semiconductor fabrication in your region, but you must have other industries. For example, if you look at this one, you use it's a pointer. Almost every household has some non-stick cookware, for example, and a lot of families have waterproof, raincoat, for example. You go to KFC, you go to McDonald's, you have this food packaging for sure, right? And of course, you use a fire extinguisher. You use biocide in the homes. So that's why they are very ubiquitous and pretty much everywhere. So as an environmental chemist, I'm a chemist. So we are trying to figure out where they are and what is the impact to the environment and how we can better manage them. So this is a figure on the left showing like how much do we have in the environment. Like it is not one single compound. It's not like arsenic. You have a few chemicals toxic, but the so-called PFAS chemicals, they are a family of thousands of or more than 10,000 different chemicals. And that is very challenging because if you are tracing one contaminant, for example, if you have lead, you know what you are dealing with. But if you have 10,000 different kind of these contaminants in water, in rivers, in the environment, it's just so difficult to manage. Okay. And then if you look at the right part of the slides, there are some examples of how this could eventually impact the environment and also human health. This is a figure I took from the US CDC. There are impacts on, for example, kidney, on pregnancy, on liver diseases, and also on heart disease as well. Why it is a concern? Because it is in most waters you can think of. And if we drink the water, and that is causing environmental exposure to human. If you have those chemicals in the air, you breathe them, that is inhalation, that is also exposure. If you swim in a lake or on the beach, they have these chemicals, there are thermal contact via skins. So they do have ways to reach us somehow. And that's why it's so important to really manage them and try to reduce the usage of these chemicals and try to find ways to reduce those chemicals so that we can better manage them in the environment. So I'm going to give an overview picture of the impact of these chemicals in the environment and what we're doing now, trying very hard to resolve these problems. So first, if you're familiar with the biology and microbiology, you know that when you have chemicals, there is this different trophic levels. You have this term called bioconcentration or bioaccumulation. So in this slide on the left, I give some examples. If you have different trophic levels and then the concentration of these PFAS chemicals, they will of course increase with increasing the trophic levels for sure, right? These are some data collected from some states in the US, from New Hampshire, for example, and showing you that the bioaccumulative potential of these chemicals, which means, eventually you have a little bit of those in water, and because we are on the, higher end of the trophic levels, there will be accumulation. That is also exposure. There are a lot of scientists already trying to figure out the concentrations of these chemicals in fish, in seabird, for example. So those are being extensively studied. Of course, they were able to detect, in the meat, even in fish, they can detect certain levels of these chemicals. So conclusion from this slide is that, of course, they could accumulate. If you have those chemicals in the environment, they could accumulate in water and to other aquatic life. So this is a tricky one. Now we have to think about, eventually when we talk about how they impact human health and the environment, that is toxicity. But we never, we do have epidemiology, for example, that is a more statistic approach, but we don't really do experiment or health experiment on humans, right? So we do have some data for smaller mammals to look at the toxicity effect. In the middle of the slide, you have a few of those impact of these chemicals based on chronic exposure. For example, you have a cup of water today. This water contains some levels of these volatile chemicals, and you drink them, you don't really feel much difference. But if this is a chronic, prolonged exposure, that's when we are more concerned. And of course, on the molecular level, there could also be impact when those molecules are uptaken by us and enter our body and the cells, causing problems. So on the left, there are some exposure pathways. For example, if you have them in the water, when we drink water and when we breathe air, and also from our swimming activities, wastewater treatment plant leachate, those could always come back to us if they're not well managed. So conclusion is that they have potential toxicity, but of course, we don't, for environmental scientists, we don't have the direct data from direct human toxicity. So what are we doing now? Like, I have been paying close attention to the regulations all over the world about these chemicals. Like in Europe, of course, they are more they have more stringent regulations, and in the U.S., like the Environmental Protection Agency, they are proposing those regulations. In the water people drink. Okay, so those are the concentrations. You have, for example, you're allowed to have 4 nanogram per liter. You can think of nanogram per liter, or nanogram in 1 liter of water. That is extremely low concentrations. For PFOS, for example, those are on the left. Those are the acronyms of different PFAS chemicals, and for some of them there are 10. Some of them there are 4, which is extremely low concentrations. This is the regulation from last year, and the entire scientific community, and also the water industry and other industries, they are trying to comply with these regulations. So there are ways to tackle those problems, of course. But the first thing is that how much do we really have in water, right? Because you see, the government, they allow like 4 or 10 nanogram per liter. How much are we looking at in the environment? Right? Knowing that is very difficult. You have to take the water sample. You use very advanced instruments and to analyze those chemicals. So, for example, these are some activities we're actually doing in my lab as well. We're trying to figure out, like, if you just grab any water, any soil, sludge or sediment, like how much of these chemicals do you have out there? So we use a very advanced method and instrumentations to analyze those chemicals, and this is one of the standard method. And then we have another one. So we have two set of methods. One is to analyze the water we drink, drinking water. We do a lot of extraction, advanced mass spectrometry. The other one is more complicated. We are looking at so many different things like soil, wastewater discharge. The first figure over here is biosolid, right? So I'm not sure about the practice in Indonesia, in many countries, including over here in Ohio. Those biosolid from wastewater treatment plants has been used as soil amendment in agriculture, and we also analyze those stuff, and of course we can analyze how much of those chemicals are in fish, for example. So with those methods, we're able to figure out like how much we really have, what is the problem there, and based on that, the scientists started to look at their impact and management. Those are some methodology as well, just to let you know, like it's very difficult to analyze those chemicals using a lot of complicated instrumentation, and that's one of the challenges for the water utilities. Nowadays a lot of water utilities in the US, they're actually trying to purchase those instruments so that they can analyze those concentrations themselves to make sure that the water is ready to go without much levels of PFAS contaminants. This is an example. I was talking about we can analyze those samples. And how much do we have eventually in the environment? Do we really have those chemicals, or are they just imaginary? Of course, we do have those chemicals. So this page is showing an example this is in Florida. This is in the state of Florida, looking at like different counties. And they also have military sites. The military sites, they also use some of those chemicals. As you can see, they are very widespread. This is only for the state of Florida. You see different concentration levels, some going as high as 10,000 nanogram per liter. Of course, this is not for drinking water. Drinking water we only allow around 10 nanogram per liter, but in the environment, you eventually have a lot of those. And again, on the labs is another figure showing you why eventually these contaminants could come back to us, right? For example, if you have like landfill, you have these contaminants in your landfill stuff, and this leachate goes to wastewater. After treatment, it goes to the environment. And in the environment, if you drink surface water or aquifer, which is groundwater, eventually they come back to us for drinking purposes. That's why it's very important to make sure that they go all the way, but they don't really come back to us. So that must be a way to block those chemicals. Otherwise, we have exposure. So this is a concentration level example in Florida. And this is an example from where I am. So this is our analysis of samples. This is by one of the students in my laboratory. So we are trying to figure out like how much we have in our nearby environment. So we took most of the samples from around the city of Cincinnati, which is around here, and there's a river. There are around 5 million people drinking water from this river, which is called Ohio River. So along the river, we take samples. We also took samples from the Great Lakes area. This is around Chicago. This is in Indiana. But most of the samples are along the river. So as you can see now, in those environmental waters here, you have very high levels, but you think that's not so relevant because eventually you don't drink that water. Okay, so over here, the data I'm showing is that people do drink from this river. There are around 5 million people drinking from this river, and we do still have, relatively high concentrations of those chemicals as well. Okay, so those are some very fresh data we obtained from places near our community. But then if you look at globally, like there are already a lot of research going on in this area. In terms of the numbers, like monitoring numbers, of course, like US, China, they are leading in numbers because there are a lot of people working on this. The very early research on those are actually from Europe. They start much earlier in terms of monitoring. But in more recent years, in China, Australia, US, there are increased numbers of those studies. So there are already a lot of those studies, but of course there are areas without data at all. There are many countries like without any data, but we are sure those chemicals are there. Okay, and on the right, it's showing you different chemicals. If you are interested, you can do some quick research. These are different categories of chemicals that has been being studied in the past. But I think this number is still increasing. There are a lot of more research in this area for sure. And this one is just to show you how they move around in the environment. Just to give you an example, if you dump something on the floor, on the ground, or in landfill, and you think you might have this kind of chemicals, and when it rains, you have storm event, this rainwater could flush those chemicals downward. If they can travel deep enough, they can reach the groundwater, right? That is causing problems when people drink water from a well, right? So that's why sometimes in groundwater, they are able to detect. Since if we drink water from wells, we think maybe it's cleaner than water from the rivers directly, right? Which makes sense in many other parameters. But in terms of those contaminants, they are pretty much everywhere. Sometimes we do see some of those PFAS. They have even higher concentrations in well water, for example. This table is little condensed. It is compiled by a student in my group before. So the objective is to show you now. I've been talking about like in water, we have this contamination. Are we able to get rid of them? So in this table, I can quickly explain, pretty much these are data showing that, okay, you have those concentrations in the inlet, which is the raw water. And after treatment, you think maybe you don't have any left, but actually the fact is, those numbers persist. Okay, you still have considerable numbers of those chemicals, which means, if you send your water to wastewater treatment plants, it's not going to help you remove those chemicals. It can slip through. But this is wastewater. But what's more concerning is drinking water, right? You think a drinking water treatment plant is pumping water from the lake, and after treatment, the water is clean enough. And I can show those some data from countries all over the world. So this is the raw water they take, so they can treat those water for people to drink. And then you look at after the water is ready, this is the water that people can receive from taps. And you can see that there's not much difference, right? So the numbers are pretty much equivalent, which means even your drinking water treatment plant is not doing anything. Like if you can, for example, in Ohio, if in the Ohio River we have these chemicals, which means we will have them in our drinking water as well. So that is the problem. Why it's eventually causing so much problems, because we cannot, properly manage them. So this is another figure just to show you that, the concentration, when water starts enter from here, the concentrations don't really change much. See, you are not able to really remove any of those chemicals. So eventually, after this step, this is the final tap water, which is the water we drink. So yeah, that's the challenge here. And we have to do something about that, right? We have to do something eventually. I'm an environmental chemist again, so we have to look at how we can better manage those chemicals. It will really help you capture those chemicals, which is adsorption, which is still the most realistic way nowadays in many countries try to remove those chemicals. Okay, so that's also what we're using in the city of Cincinnati. We're also using granular activated carbon, try to remove those chemicals from drinking water. So in some countries, in many countries, they also have the point of entry treatment facilities. They have the device, the water comes in, and this device can further remove something from further purify the water. And that's also another way that could help us try to reduce the risk to these chemicals, right? So these are called anion exchange reagents. These are very small particles. Pretty much those particles have size that can absorb these PFAS chemicals from water. To some levels, they also work pretty well. Now we have to think about this. Okay, so we have these chemicals in water. We're trying to remove them from water, just like you are trying to grab something from water so that it's no longer in the water, but it's in your hand. What are you gonna do with these chemicals in your hand, right? You cannot keep it. You need to put it somewhere. And then you think I can use water to flush it down. Then that's the bad circle. You are flushing it back to the environment. It comes back again somehow. So we need to find a way to destroy it. As I mentioned it from the very beginning, we can destroy it, but very difficult because they are designed to be extremely stable. So just to quickly show you some ways, it's very expensive, but there are people already developing method to destroy them. So for example, the first example, there are already people trying to use this in a real application. These are the first one I want to introduce is the hydrothermal conditions, where actually you have to heat up your water as high as 300 degrees C and above. Of course, you have to give higher pressure so that the water is in a supercritical condition. In that condition, these chemicals can be destroyed. So you can imagine how difficult it is to destroy these chemicals. You need a 350. You need a few atmospheric pressure to achieve that. Expensive, of course. Another way people have been using is using some light. Okay, so light generates photons, high energy photons. Eventually, even water, we can split water with the high flux of photons, right? We can also destroy those chemicals, like break the chemical bond. Eventually, they becomes fluoride, they becomes ions, and that resolves the problem as well. So actually, this one is also very warm data. Somebody from my lab actually he developed something also very interesting. He developed something that could, when the water comes in, can capture the PFAS into his magic materials, and after that, just heat up a little bit, this PFAS can be destructed. As I mentioned earlier, that people have to heat up to 350 degrees C, and we don't have to. We need a much lower temperature to be able to destroy all of them. So eventually our objective is to capture them and make them mineralize so that there is no problems anymore. So of course, there's still a lot of challenges we're trying to address, because of course the first thing is that they are very persistent. It's very difficult to destroy them. Something I didn't mention is that in the environment, it's trace levels is very low concentration, right? It has chemical diversity because, as I mentioned, you have more than 10,000 different species, right? It is surfactant because it has a charge. It also has a hydrophobic gel. And also humans have many ways of exposure. If you figure out, okay, you can remove them from water, but some of them are in the air, in our working spaces, I'm just giving an example, making up an example, like from our air, for example. So there's also complexity of exposure. This is an ongoing research in many countries, but finally, the best approach is if you don't use this chemical anymore, right? Just get rid of it from the very beginning, and then the problems can be solved easier. But we know that not only in the US, in any countries, that is almost impossible. Like, okay, tomorrow I can tell all the manufacturers that let's stop manufacturing these chemicals. That is not easy to do. So those are pretty much those some summaries about the current scenario or landscape of this kind of research, and how this could eventually impact environment and also human health. So I just want to take a very short time to talk about things like what are things going on here. So like for my lab, we are focusing on emerging contaminants. Of course, we are in Cincinnati. Those are some photos we take in the past months and years. Like we have folks working on analysis. We have folks working with destruction of chemicals, monitoring toxicity tests, treatment, and pretty much a lot of field trips. And these are some of those photos. And as Marcus mentioned, we do have we got some funding in like American Chemical Society, some industries like the semiconductor industry. We have something I didn't mention is that we study a lot of stormwater or rainwater. I know in Indonesia, of course, you have a lot of rainfall, and you have runoff on the road as well. So something very quick about where we are here. So on the lab, I took this is a flyer for grad students from 2 or 3 years ago. These are some of our faculty. We have professors in water. So we have water, we have biology, we have hydrology, we have sustainability, we have renewable energy. So those are the directions we have here. And I'm also attaching a few photos of the university. So this is the university, and this is the city of Cincinnati, and this is also the city of Cincinnati. So that's pretty much those information I want to share with you, and if you are interested in using this.
Okay, thank you, Dr. Neil, for the great presentation. We have a very strict time actually. Based on the schedule, we should be finished by 11, but because we start quite late for your session, so I think we still have 5 or 10 minutes for the discussion. And then for the additional information for our view, Dr. Neil has a research group consists of 8 students. The combination between PhD, masters, and also undergraduate students. He also also have his own lab, and then we keep it with a very sophisticated instrument. He has a LC, MS, double MS actually, and also so many other sophisticated analytical instrument as well. So basically, Dr. Neil has everything he has in his research groups to be very productive. Okay, do we have any questions from the audience? So actually PFAS is very problematic, right? I try to be honest, I also don't really familiar with PFAS. I just know, yes. Do you have any questions?
Doctor? Okay, thank you.
Oh, yeah.
Dr. Cicinings. Yes, Cicinings. Okay, sir. I know that you're discussing about the PFAS in the environment. That's maybe my question is a little bit outside from your topics. But we know that you're discussing about the PFAS that we call chemical chemical forever. That means that will easily to be degraded. So we know that right now it is very popular that people using the non-sticks cookware. Usually because it's very popular now. So I worry that PFAS from the cookware that we are using for frying, for example, can release to the can release from the cookspares. So goes into the food we are frying. So maybe you have suggestion for us that we should continue to use the dead non-sticks cookware, or we just left it. Thank you.
That's a very good question. First, if you ask me if we should continue using that, I'm still using it, okay, in my home. So I'm not in the position to, to say, okay, we should stop using that. It's really a personal decision. Now, regarding your question of whether it could enter our food, I can tell you is that there is no direct evidence. So we're talking about cookware because we know that those cookware, the Teflon layer when we cook, which is non-stick, that is made of those polyfluorinated compounds, right? But you don't have direct evidence saying, okay, you're cooking and this chemical comes out, right? We only know, okay, this is a source. But if this source really releases chemicals, it depends, right? So it's like you have a flammable chemical, but it doesn't have to explode. But it's there. There's a danger. So there is no direct evidence for that, but there are active research on that. For example, there are research like if you scratch the surfaces of this Teflon layer, and of course the chance will be higher. Like people start to use a lot of water to rinse these scratches, and eventually, of course, they can find some. But nobody is going to cook like you scratch your Teflon layer and flush it. But I'm just giving an example. It's a source, but it doesn't have to come out. So I hope that answers your concern. But again, I'm still using those cookware in my home, so to be honest.
Okay, thank you.
Yeah. One more question from the audience, if there is.
Thank you very much for the time. Thank you for your presentation. I am interested in technology removal related to PFAS to contaminant soil and wastewater. I am research about chitosan. Chitosan we hear a lot of stream waste with its potential for absorption material, environmental friendly absorption. Maybe do you think about using chitosan as absorption material was water or soil? Thank you.